my name is Ofer, and I'm going to talk a little bit about large language models today and grounded generation, which is what we do at Vectara. So a little bit about me. I'm running developer relations at Vectara, and you can see a little bit of the other experiences I've had in the past. But one of the reasons I'm talking to you about this today is because I've had the chance to work on large language models for a long time before, November of 2022, right? So I think everybody knows about it the last 6 months, but I've worked on this for about 4 years. And in fact, my first large language models that I've used was the early days of GPT-2, which is kind of cool. So I'm going to show you a little bit of GPT-2 and how different it is than GPT-4 in a little bit. So I'll start from the beginning, right? Again, I expect that there'll be a mix of people here, so I kind of going to start there. So what is a large language model? A large language model is essentially a really big, that's why they call it large, neural network that is trying to understand language. And there's different use cases. You can sometimes want it to summarize things, sometimes to translate from different languages, predicting things about text and generating text, which is what we all talk about recently about Gen AI. So there's a couple of flavors of LLMs. We talk about there's a decoder only, encoder only. Oh, I actually got those wrong. I'm sorry. Encoder only is these guys, and decoder only is these guys, the GPTs. And there's encoder, decoder, and there's something called embedding. And so you hear about these different types of models, and we'll talk about them a little bit later too. But these are some of the names, and the picture here is much more complicated than that. I'll have a more complicated diagram in a minute. But those are the one of the way you distinguish is by which architecture they have. And so those are the type of architectures that you can think about. Now, what is a GPT style language model? That's the one I call decoder only. We also call this an autoregressive LLM. Autoregressive because it generates stuff, one step at a time. So what it does is you take a bunch of documents or text of any kind. Usually people train these models on these Common Crawl or Wikipedia or anything like that. And then you use this transform-based neural network, which I'll explain what it is. You train this on all this text. And then really what you're trying to come out with is a mathematical equation, which essentially means I want to predict the likelihood of the next token, given everything that happened before, all the tokens in the past. T1 to Tn are like all the tokens. And so you do that one step at a time, and you can think about a trained network as something that can estimate this probability really, really well. Okay? This is really what's in the training. So a little bit about history, right? So there was the big attention is all you need paper that everybody's talking about, and then there was a kind of a funny thing where we said something is all you need. Like there was 15 papers that took that thing and created fun things about that. But then GPT-1, they didn't call it one, it was GPT, started around this time. Bird was very popular, GPT-2. There's a bunch of other names. And we've been having a lot of progression in these models over many years. But really it started from this big attention is all you need paper that really changed the game. And the reason is because of this transformer architecture. It was really, really important. And what it is I have this really big diagram here for you, and I'm not going to get into it. But if you want, that's a whole hour paper on its own. But essentially, that is the famous diagram of the transformer, which has a couple of things I want to talk about when thinking about this. One, it is a specific architecture, right? Neural networks, initially when we started doing them, 20 years ago, was like every neuron connected to every neuron. And the idea of creating a specific architecture is constraining the connections between neurons in a way that makes it easier for them to learn a particular thing. Now, what the particular thing is, there's a vision, there's text, there's all these kind of things, and a lot of architectures for text were suggested over many years. The transformer one really made a breakthrough and made everything so much easier and so much better. And that's really what what is meant by this when I say architecture. It's a particular way to structure the network. So inputs are tokens, right? Tokens could be words, could be subwords. I'll mention something about that later on. And the outputs here are going to be probabilities. Like I said earlier, the probability of the next token, given everything it's so far. And it uses this thing, again, a little bit terminology of self-attention. So this is it says multi-head attention here and mass. So this is the self-attention is one of the mechanisms in the transformer architecture that allows it to learn very well kind of backwards. And so the word attention, the way people think about it is sort of like I'm generating the next token now, and I'm able to pay attention to whatever happened in the past. Meaning some words can be important and some words may not be important. If I learn, for example, the sentence, the boy went to the, and I'm trying to predict the next token, that token could be related to the fact that it was a boy, maybe not a girl. And the word went to is interesting because so it pays attention to the parts of the sentence that are interesting and maybe doesn't pay attention to parts that are not interesting. And so this whole attention mechanism was, again, a key breakthrough that made understanding of language really, really useful and effective in how transformers and how language models work. Okay, so that's as deep as I'm going to go on that. But I just want to give you a little bit of the terminology. I think you hear this all the time. And people are like, yeah, attention, transformer, people talk about it in machine learning so much. This is kind of what it means at a high level. I promised a much deeper diagram. This is it. I picked it from somewhere. There's so many models that have been developed, both open source and closed source. The branches here, I think, are marked based on whether they are blue is like the coder-only models, the GPT style. I think green is the encoder-decoder, like bird, not bird. The encoder one is bird is this side, and this is the encoder-decoder model. So there's a lot of different architectures, and you can see, and this will continue to happen, right? And interestingly, the open source community, I would say, unlike today, where there starts to be a little bit of a closed source mentality, but in initial phases, there's a lot of collaboration and a lot of people work with each other to kind of continues to make these things better and better over time. So I talked about tokenization. I want to talk a little bit about that. What does it mean? So again, to be a little bit more specific. So let's say we have this sentence: you should never take more than you give, right? So first, we break it into words. You should never take more than you give. And then neural networks don't actually understand text. So what really happens underneath the covers is every word has a number, an ID. And it's usually some kind of fixed vocabulary. GPT is like usually 50,000. It's actually subwords. I'll talk about it in a minute. But let's assume it's words for a second. So you take the sentence, you break it into these words, and then you translate it to the numerical value of that word. And that's really what gets into the neural network. Now, this is my animation I made for all of you. But what happens is you take these vectors of IDs and you move them through the network, like you do a forward pass and a backward pass with back propagation, and the network gets trained. Now, again, there's 3 here, but imagine, billions of these little snippets of text that gets translated into vectors. And that's really what training means when you train a model from scratch, right? When people talk about the fact that neural networks like LLMs are really expensive to train, they mean this process right here. So you train from scratch. You start, the weights of the model are randomly initialized. And then it just starts to train and learn this probability distribution we talked about earlier until it knows how to do that. Once you do that, there's other things that you can do called inference, which I'll talk about in a minute. But before that, I wanted to convey a couple more concepts that you might hear in this industry that are important. One of them is called fine-tuning. Maybe you've heard that name. Who heard about fine-tuning? Raise your hand. Yeah, okay. So to explain fine-tuning, I want to also talk about transfer learning. Transfer learning is an interesting concept that I worked for many years as a machine learning engineer, data scientist, where what I call traditional learning, for lack of a better word, using random forest or gradient boosted trees or whatever else. And traditionally what we did is we took data and we trained on a particular task. Like I want to classify if something is, negative or positive intent, or I want to predict, something numerical or something like that. Now, that's still good. That's a way to do it. But if the training is very, very expensive, transfer learning tries to make that an easier process. And the way it works is you train a model on a more generic task, like I showed you earlier, like learning how the language works. And then you want to transfer what you learned at the end towards a particular task. So the way it works is you train, for example, a large language model here, like I showed you earlier. It's long and it's expensive. And then you kind of take the knowledge that was obtained there and you do a little bit at the end to adapt it to a particular task that you wanted to do, like classification, summarization, or sentiment analysis. And there's a couple ways to do transfer learning. One of them is called fine-tuning. So if you think about fine-tuning, it's a type of transfer learning, right? That's why I told you all of this about transfer learning. With fine-tuning, you take a pre-trained model and you continue training it for a while. Usually on a smaller, maybe more specific data set. But it doesn't have to be. But usually it's maybe a different data set or a smaller data set or something like that. And there's a variety of ways to do fine-tuning. For example, you could continue to train it completely, the whole network on a different data set. You can also freeze some of the initial layers and then freeze some of the layers and continue training on some of the later layers. You could add a layer for a specific task. There's a bunch of different ways to do it. And they're not all equal. So, a lot of expertise there needs to be to understand which one you would want to use. One recent advance in fine-tuning that I wanted to mention, you might hear this if you read some of the papers, is called LoRa. It's kind of quite interesting because it allows fine-tuning to be more efficient, and since for low rank adaptation, but it essentially makes fine-tuning faster and more efficient, and makes it, because fine-tuning is not easy. You have to have expertise. You have to know you have to have similar expertise to when you train a model from scratch, because you have to know how to stop it and what learning rate to use and things like that. Last thing I want to talk to you about is, we train a model, great. Now I want to do what's called inference. So we want to predict or summarize or do something with it, right? That's called inference in machine learning. And in the LLM space, of course, what we do is we generate tokens one by one. Then you can start with a empty sentence, but in this case, I'm going to show you an example of, I start with a half of a sentence, like the sky is blue because. And then what happens is you say, please give me the next token. And it predicts some of the possible next tokens. It's kind of a stochastic thing. So it's not always one token is possible. There's a list. And each possible token has a certain probability to it. So then it samples from this probability. So let's say the next one was of. And then it adds that token to the sentence and does it again with the next token, right? And he does it step by step until you tell it to stop or until it completes the sentence. Now again, every one of those now is conditioned on the rest of the sentence so far. So it's why it's a step-by-step process like this. All right. So now, since I told you I was kind of early on in GPT-2, I wanted to show you like a real demo of what GPT-2 looks like. I don't think a lot of people look at that anymore. So, is this showing okay? I'm just gonna make it a little bit bigger. Okay. So this is the Hugging Face Transformer library, which, by the way, was a great library from early days in this space. They made everything available to everybody. So what we do here is we load a GPT-2 tokenizer, and the GPT-2 model. Okay, so we kind of load them in. And then after that, what I have here is just a little bit of Python code. So first, I create a tokenizer and a model, and I say, please generate those. And I have a certain prompt. This is my beginning of the sentence here. Larger language models hallucinate because, right? And then you take, and I showed you how the words become tokens, right, or IDs. So this is where this happens. You take the text and you actually encode it into individual IDs or numbers. And then I can, let me show you how this looks, okay? Right, here we go. So in this case, you see, and this is why I wanted to show it, because people talk about tokens as if they're words, but actually in GPT it's not words, it's subwords. You can see an example here. Large, language with a space, models with a space, halluc, innate, because, right? So it has a certain way that it actually, this is called byte pair encoding, is the technique they use. There's a lot of ways to do tokenization. This is a very common one for OpenAI and all the GPT models, but Google uses other techniques, for example. And you can see that every one of those words is in the vocabulary and it's got some number, right? Some ID, right? Now, the next thing I want to do, of course, is I'm going to now generate the continuation. Now, in this case, I'm telling it, please generate, given these input IDs, generate no more than 50 new tokens. Again, not necessarily words, it could be subwords. Let's do that. So what happens now is it generated these output tokens, as you can see here. And I also decoded this, translated it back to tokens. So you can see the actual words that it generated. And of course, I can, for convenience, put it in the sentence back. But that's really what it looks like. And I thought this would be like a good sort of demonstration of what's underneath the covers here, right? So when people say they generate, this is kind of what happens, right? All right. So now I'm going to talk about hallucinations, all right? Why they happen and all that. So people argue about the definition of hallucinations. I think of it as mostly terminology. So for example, so one definition I like is, when the generated content, which is generated stuff with GPT, is nonsensical or just not or unfaithful to the provided source content, or just something that we look at or read as humans and we say, yeah, doesn't make sense, right? Some people, I see a lot of people argue about, it's got to be called fabrication, or you can't even call it something that's based on human notion because it's, things like that. Fair, maybe. I think of it as just terminology. This is the word that's been chosen by some machine learning engineers or researchers that started seeing this and they just call it that. So think of those as completely, the same in terms of it's just terminology. So we'll call them hallucinations. And this is an example I wanted to show you. So I asked ChatGPT just a couple of days ago, did Will Smith ever hit anyone? Okay. There's no public record or credible evidence to suggest that Will Smith ever physically assaulted anybody. It's important to be cautious when dressing, You can read it for yourself. And of course, we all know what really happened, right? So, so that's really what a hallucination looks like, or a type of hallucination, right? Usually this happens, right, when the LM didn't know about this fact, right? And we'll talk about this more in a minute. So I wanted to go into and explain two kind of broad reasons, the way I think about why LMs hallucinate. So before I do that, I want to explain this concept of a knowledge graph. And a knowledge graph, I apologize up front, it's a kind of confusing terminology. A lot of people think of a knowledge graph. It's been used in machine learning and analytics and a lot of other contexts. So don't think about it as that. It's just a tool I'm going to use to explain hallucinations for you. But if you think about a larger language models, after it's been trained, it has some kind of retained knowledge that it learned from the source data. That's what I mean by a knowledge graph. It doesn't actually have to be a graph. We don't know how it's actually, there's no tangible form of it. It's embedded in the weights of the large language models, the billions of weights that are there. But I think of it, to make it simplified in my head, as a knowledge graph. It knows like maybe events and connections and, as a probability, but that's what it can do. And so when you ask an LLM to respond, in some sense or another, if you want to kind of abstract it out, it relies on the knowledge of what it learned from the source data to create a response. And as I said, we can't really understand what the knowledge is. It's you can't open up the neural network and see inside what it is. But as we use it, we observe kind of parts of its knowledge, right? Anecdotally, right? And I wanted to explain this concept because I think the two reasons I'm going to share is, one is sometimes you ask the large language model a question, and the answer, it just doesn't know. It's not in that knowledge graph. It hasn't learned it, right? Will Smith is a good example of that. The other one I used a few months ago was who owns Silicon Valley Bank, which was a favorite question of mine. And of course I said, it's Silicon Valley Group, and it's a great bank, and all the VCs invest in money in the startups. It's a Silicon Valley thing. Of course, it doesn't know that the bank collapsed, right? So the reason, what happens with LLMs is we saw they're just completing sentences. But they're large, they do a pretty good job at that, but they're just completing sentences. So they're not trained to think about the question and create a response. And therefore, they're not trained to say, I don't know, right? And so a lot of times they wouldn't say that. Even if it's not in their knowledge graph, they wouldn't say that. Now, I will tell you that I've seen recently a couple models like OpenAI and BART and others, where they start training them using something called RLHF, which I'll talk about in a couple slides, to sort of say, I don't know, or refuse to respond. I will talk about this more, but generally the base model is not trained to do that, right? And therefore they will try to pick the most highly probable thing they can say given the start of the sentence and complete it some way or another. And if they don't have the right answer, they'll do something else, right? A lot of times it's not that it's not that they don't know the answer. Sometimes there's also multiple answers. And you might have one political opinion and somebody else might have another political opinion, or you may have a lot of different people who respond to the question on Wikipedia or somewhere else in different ways. And so you might see a response that just you think is incorrect, but it's actually somebody else in the world thinks that way, and therefore it might be perceived as a hallucination too, right? Again, it's really responding to what it's been trained on, all right? The second reason is that it has fictional content and has, that are not according to your opinions and beliefs, right? So I don't have a good example of that to show you here, but you can imagine that a lot of controversial topics might have different types of opinions and things. And it might create a response, but the response might not be what you like to hear, right? Okay, so I promise I'll talk about RLHF, and this is a kind of complicated topic, but I thought it's useful to go through it a little bit to explain what's been done. I would say that's probably the most interesting and useful way people try to address hallucination from a research perspective so far. So for example, ChatGPT from OpenAI, Anthropic, DeepMind, they all apply this technique. And it's got some advantages, it's got some disadvantages. So I want to walk you through this to explain what it is, because I think it'll continue to be part of our world of LLMs. It's going to continue to be there. And then I can contrast that with grounded generation, so we can look at them as one or the other. So RL stands for reinforcement learning, and HF is from human feedback, right? And the idea is to use human feedback to align the LLM responses with some human provided input. So there's a diagram here, and I'm going to walk you through that, right? So the first step, kind of on the left here, is what we talked about so far. GPT-2, GPT-3, all these models, they're trained on, everything I told you about is just this left side here. You take the text, you train it to create a language model that's pre-trained, and it's trained to do completions, what we just saw, right? You give it a bunch of a text and it completes it, right? Usually you have a lot of, trillions of tokens, examples of these models are the GPT series, there's Falcon, we heard about a Llama, Stable LLM from Hugging Face, all those are that kind. That's not ChatGPT, right? They're not very good at kind of chat and answering with a question. They're just completing the sentence, right? And so I think in the last, or probably 2 years or 3 years, there's been this discussion about how do we make them more like ChatGPT and responding to these kind of things. And so I'm going to describe these 2 steps here that led us to this direction. The first one was really to create responses, and then they found the responses are not so good, so they went to do good responses, right? So the first one we call supervised fine-tuning. Okay, what that is you create some demonstration data. So this will be pairs of a prompt and a response, right? That you create somehow, and people do it different ways. Sometimes they hire people to write those. Sometimes they create them with other techniques and technology. Sometimes they have data sets that people have that create them. And it's essentially a kind of a fine-tuning process that looks at that data. This data is called demonstration data. It's just curated prompt response pairs. And they usually use 10, 15, 50,000 of those or something, and they make the model a little bit better. You heard about Databricks had Dolly, for example. That's a good example of that kind of process that they did. And a couple others, right? Now, it turns out that that's a relatively good start, but the research community thought that that's actually not good enough. And I say thought because a lot of the research here is still not, there's not a lot of conclusion. It's kind of in the middle, right? Where there's a lot of arguments about this. So I'm telling kind of the best that I know about what's going on. There's not enough years to really know what's going on here. But the RLHF is something that seems to be doing, at least people believe, a much better job. And kind of what happens here is you actually take a prompt, you choose a bunch of prompts or questions or whatever it is, and you ask this model that was fine-tuned, this SFT model here, to create multiple responses, right? Because it's stochastic, it can generate, a few of them. And then you have human reviewers, you hire people to just go through them and sort of rank. This is good, this is better, this is worse. You collect all of this information. And reinforcement learning is a branch of machine learning that actually, they call it a reward model. So you look at these human inputs and you create a reward model that can be then fed into this reinforcement loop. And I'm not going to get into the math of that today, but it's a whole other topic. But suffice it to say, what happens is it retrains the whole model backwards with the rewards to get to a really, really better model, which is what we see and we all know in sort of ChatGPT today. All right. So this is a much more complicated and much more expensive process. But it gets people believe and have shown to some extent better results with that. All right. So when you hear RLHF, this is what it means. But I wanted to tell you this because this is important, because people think about larger language models first as this thing, but they experience this thing at the other end, the ChatGPT. And there's a difference here, and there's a whole lot of process that's not so much talked about, but is important, right? So for example, if you fine-tune, remember we talked about fine-tune, if you fine-tune this, right? And you want to get to a better on your own data, for example, you still will need to do these 2 things to get to the right results. So people sometimes say, oh, I'll take ChatGPT and I'll fine tune it to something, but you still have to do these other pieces and they're not easy. And in fact, I want to talk about why they're not easy, right? Human feedback is very expensive to collect, right? You have to hire people, you have to train them, you have to make sure that they give you good responses. They can make mistakes. They have to build some technology to collect them and kind of like figure out how many mistakes they make, maybe ask different people the same question so that you can actually kind of figure out mistakes automatically. There's a lot of tricks that people do with that. Human feedback can also be biased, right? We talked about the fact that responses could have, just opinions, right? So who to hire may result in bias in the data. People talk about long-form responses. So imagine you have something we see in ChatGPT today where you ask it something and it gives like, it was a page of instructions, right? How do you know if it's better than another page of instructions? It's kind of hard to judge sometimes. There's a step before that step. And so some of these things where if I ask you who owns Silicon Valley Bank, that's an easy thing to judge. But if you have a page full of a response, it's kind of harder to judge, right? So that's part of the problem of that. Now, as I mentioned, retraining the model with RLHF can be both complex and expensive, and you need to know what you're doing. And the other thing that I kind of hinted to before is that, and if you play with the GPT-4 or ChatGPT in the last few months, you've seen that more and more it kind of refuses to answer. So instead of doing hallucination, it sort of says, yeah, I don't know. I'm just an AI bot and I'll be trained until 2021 and I don't know, kind of thing. Now, that's okay because it maybe doesn't hallucinate, but it's actually not very useful, right? Because I don't get the response I want, right? So it's not helping the user with what they're asking. And as I showed you in the example with Will Smith, right? Even RLHF trained models, it was it. They still sometimes guess, and they think they know, and they respond wrongly, right? So, okay, that's going to be all I'm going to say about RLHF, and I have a link here if you want to look later on that actually has a good, more in-depth explanation about it. But that's really the state of the art from the academic side, and how product companies like OpenAI and Google and others are sort of doing that. And I think they're going to continue to do that. And I expect that in later and later models, this will become better and better too. But I want to talk about what Vectara does and what we're going to do this, which I think is a different approach that has some advantages over this, right? So we call this grounded generation. And what it is, it's also known as Retrieval Augmented Generation, right? It helps the LLM focus on the facts that matter and provide more accurate response. So I want to show you how that works. So just a couple of how is it different in RLHF, because we're kind of going off of that topic, is one, it uses what we call chat with your data. So data could be, I know it's very popular in the web right now, chat with your PDF. My son is in college, he wants to chat with his PDF for the test that's coming up tomorrow. It's been something he asked me about. Things like that. Those are very common and very popular. But really for enterprise, I think about it as any data you have in terms of like stuff that's in your database, and any data that you could actually use for business, not just documents. Could be anything that you want. That's textual. You can ask questions about that text, and I'll show you a few examples. It's significantly less expensive, right? So if you think about data that keeps updating every day, you're not going to fine tune or retrain and do RLHF every day if you want to like add more data. So it's just not feasible and going to be completely expensive, right? So we can update data in real time. And one of the other things that I just want to mention that people are afraid a little bit about is this idea of privacy recently. Yesterday, I was at this LLM Avalanche event last night, and somebody asked the crowd, how many people trust the big companies like Microsoft, OpenAI, or Google, with their data? And the answer was nobody. It was very obvious that there's lack of trust. So the privacy issue is really important. People are afraid that if you send the data to these companies for fine tuning or things like that, they will use the data. And there's been, of course, famous leak examples in recent few months, right? So that's another angle that speaks to that. So how does grounded generation work? Well, you have a bunch of documents or JSON or text in any form you want, and you essentially, if it's documents, with Vectara, we'll extract the text out of the documents for you with different document types, and if it's already text, you can just send it directly. And we also have a nice facility in the system where we chunk the data into sentences. So if it's a big chunk of data, we do a little bit of a really nice NLP to sort of break it down to the right chunks. And then those sentences are then encoded into embeddings. For each sentence, we got this embedding which is essentially a vector representation, a dense vector representation of that sentence, what it actually means. And we store it in a vector store. So what's the difference in a vector store and a vector database? I think of it as vector database as a separate company that just does vector store. And I think a vector store is more of a generic term that can do that. So this all happens within the Vectara kind of system during indexing. So when you index, you send those documents, it goes through to the vector store. And then the second part is you want to run a query, right? So you want to do something, ask a question. You get the query into the system. Again, it runs through the same embeddings model. You create an embedding for that query. What are you asking about? That query gets run against the vector store, where all the documents are there already. And then the most relevant sentences or most relevant chunks of text that are relevant for the query can then come to the summarizer with a special prompt we put in there, and you get a response with citations of the relevant documents that it based its response on. So that's really what we have. We have you think of Vectara as two simple things: is the indexing API and sort of the query API. So what are the advantages of grounded generation? Well, it allows the LLM to respond based on recent important facts, right? So you can imagine that whenever the query happens, right, it pulls out the right fact. So that's what makes it different than something that's been trained, and whatever the last time of training is, that's where the information is. So the knowledge base can sort of, I think of it as almost like augmenting the knowledge base kind of in real time, right? It's inexpensive to implement. You can do it kind of in real time. And I think it's complementary to RLHF in a way, right? I like the RLHF, continues to improve the sort of the large language models in a way. It's not kind of this or the other. As much as ChatGPT and other types of models continue to improve, the ground generation will continue to improve as well, right? And of course, as I said, data is not used for training at all. So we don't actually need to use the data for training. Our retrieval models are trained on only public data. And a key to the success really of this is the state-of-the-art retrieval model. And I'm glad we have Amin here, who's in the audience, sitting, one of the founders of the company, and he actually developed this state-of-the-art retrieval model back in Google. So knows a lot about this. So if you have questions about the retrieval model, you can ask him afterwards. All right. So I'm going to go now into a couple of demos, okay? A little bit more hands-on and show you a couple of different things. So I want to start with showing you one example, which is this application, the sample application we created called AskNews. I mentioned the example of Silicon Valley Bank, for example, things like that. Right, so this is a live app that you can actually use. You can go to asknews.dem or Vectara.com and ask any kind of questions. This is really a demonstration of what you can build with Vectara, right? So we ingested here a bunch of news articles from these 5 sources: BBC, NPR, Fox News, etc. And it keeps recrawling every day. And you can ask it different questions. So for example, I can ask about what was introduced in the latest Apple event right here, right? And you can see that it pulls a bunch of results that are relevant from the news, right? These are the what we called earlier the relevant facts, right? And then based on those, it creates a summary using this information, right? So of course, this is a good example because this, 2021 is not, if you ask ChatGPT, it'll probably auto refuse or it'll give you something from the 2021 Apple event and not the recent one, right? And then, we have a couple of nice features that you can filter to a certain, filter like maybe just the BBC or the NPR, etc. And I'm going to show you an app step by step here that's actually doing something even more interesting. So there's a data set called the Yelp data set. Maybe some of you know it. It's kind of available for demo purposes. And what I've done is I've uploaded this data set. It's got restaurant data and reviews. I've uploaded those into this laptop's Postgres. I put a Postgres database here and uploaded everything. And to show a few examples, these are some of they have there's a couple other features, but I just looked at business name. There's some review text about this. Every row is like a review of a certain person about this business, and the city, the state, the postcode, etc. And what I'm going to show you is we're going to build a sample app just like AskNews, showing you the Vectara API and a couple other tools that we can use to search on these reviews, right? Very interesting thing to do. So to start, before you can use Vectara, you have to sign up. So generally I'm signed up already, so I have an account, but if you go to this, so I'm gonna have to go to Safari where they don't recognize that I'm signed up, but you can just sign up. It's very easy. You can sign up with your information, or you can just sign up with Google, right? And then now I'm gonna go to my console, and after you sign up, I have a bunch of different corpora here, but you can define different, create a corpus for Yelp, etc. And once you create, you can create a corpus. You can give it a name. You can give it. I'm not going to create now because I have one ready already, but you can look at any one of these. This is a nice one I just created yesterday for Game of Thrones, by the way. Kind of an interesting. A set of text too. Again. And you can look, you can create a key, an API key that you could use to access the API here. There's a search functionality here, which is kind of nice. So once you load something into this is not meant to be your user interface. It's just meant to be a testing ground where you can run some queries and see what things, anybody want to ask something about Game of Thrones? Yes, no?
Is winter coming?
Is winter coming? Okay, thank you. So it's got something from season 1, episode 1. That's good. Apparently there's something in season 5 too. Winter is an inevitable event in the fiction world. So anyway, so this is meant to show, and I wanted to show you this because it actually shows you a lot of debugging information too. So for example, it shows you for this result, the score of the relevance was this, and this is the ID, and you got some metadata here, etc. So this is, when you use the product, you should use this tool because it gives you a lot of information kind of to debug things. But this is not where we're gonna do. What we're gonna do is we're going to create a corpus about Yelp reviews and create an API key. So I'm just showing here as screenshots, and I created this already. And then I explained that the API, right? The Vectara API has 2 components. It actually has 3. There's also an admin API, so you can actually programmatically create a corpus and lead a corpus, things like this. It's easier to do in the console, but if you want, you can actually programmatically do that. But the more useful ones are, of course, the indexing, where you have usually we use the standard indexing API, which you take a bunch of text and upload it to the index. We also have a file upload API, which can be useful if you have PDFs or PowerPoint or other types of formats, which we will strip automatically and take the text from. And there's also a low-level API, which is really for experts where you want to have more control about what's going on. And then, of course, the query is where everything is indexed and you want to like read information from that. So the documentation are available. I'm not going to go into the details of this, but what I wanted to show you is what the standard indexing API looks like. And I hope this is big enough. So this is an example with Python code, right? You define your customer ID. So when you sign up, you get a customer ID. We have a corpus ID, which identifies the corpus you have. In this case, Yelp had a certain number. And then you have your API key that I showed you how to generate. With those three things, this is the endpoint for indexing. And essentially, you can create a document. A document is sort of like a JSON structure where you have your document ID. You can put a title. You can put some metadata here. And the document is a set of sections. Each section could have a text. It can also have metadata for that section, but I dropped it here in this example just for space. And it's a list of these, sections. You can have 1 or 100, right? It's like whatever belongs to this document. And then, in a typical JSON form, I call the post API call with the endpoint, give it the data of the document, and once it returns, the document has been indexed. And that's it. It's very, very simple. Just specify what you want and you run it. Now, usually people use this, right? But it turns out that getting to the data sometimes and preparing them in a document, is not always easy because there's a lot of data sources. So we created actually an open source project that you can use if you want, called Vectara-Ingest. And it's open source, it's available on a GitHub repo. And what it does is it helps with that. So it creates a bunch of crawling software that can crawl information from a database of any type. It could be RedShift or Postgres or Snowflake, whatever you want. Crawl information from a website, if you want to crawl your own website. You can crawl information from a Docusaurus, like a document website, or Notion or Jira, a bunch of different other sources. This is useful just to use as you want directly, or you can actually use it as a reference of how to use the API, which kind of has example by nature of being there, right? And so I want to show you how to use that, Vectara-Ingest, very quickly. So I'm going to go into my Visual Studio here. So this is an example of the configuration file I generated for the Yelp reviews, right? This is, there's 3 sections here. You see, okay, or should I make it a little bit bigger? The first one is the Vectara section where you put in a corpus ID, a customer ID, and this is a flag that says reindex. And so it's kind of useful if the document already exists and you're indexing, you kind of tell it whether you should remove the old document and re-index it or not, or it's fine. So if you have something that might change, like a page that has the same address, but the content might change over time, you might want to re-index it. In other cases, you don't. Then the crawler type is what crawler we have. As I said, there's different types of crawlers. This one's called database. And then the database specific parameters here. Here we have kind of a local host connection to the database I have. In Postgres, I have the database name. And you can actually define some conditions. So I chose here, I really wanted to have the San Francisco city here because we're in San Francisco, but apparently the data set doesn't have San Francisco. The sample data set that provides. Hey, Yelp, of course, has a lot of reviews of San Francisco, but it doesn't have. So I chose St. Louis, I don't know, I picked one randomly. And then you can also tell it, how to create documents, right? So we have multiple reviews. So what I chose to do here in this example is group all the reviews about a certain business as if it was like one document with all the reviews kind of together, etc. And so what happens is it'll create a document that has, for every business, the business name and the review text as individual sentences in the document and put it into the index. You can do it other ways. That's the simple way I chose to do it here. And it also includes some of the metadata as well. So that's really how you generate the config code. It's very simple. And then you could go to, and I have here an example of Vectara-Ingest. And what I could do is, sorry, I'm going to run this like this. So essentially run a command line that says, please run Vectara-Ingest, give it this Yelp reviews configuration file. And this is a name of a key for a secret. So we have a secret file where you put the API. We don't want to put the API in a place where it's part of the code. So there's a file called secrets.toml, and this refers to that secret. So once you do that, and I can start running this, it runs a Docker instance on your machine and starts the process. Given that this might take an hour or so, I'm not going to run the whole thing now. But generally, that could run for an hour and do all the create all the things that it needs to create, run all the ingest process. A lot of times, what we do is we put these on a virtual machine somewhere that it gets kicked off like every day or whatever. Things change dramatically, and you can kind of index, re-index every time you need to. All right. So I'm gonna stop this guy. So in terms of size, we have kind of the growth plan, which is our kind of the basic plan for Vectara. And that has a free tier that I think is up to about 50 megabyte of text and allows you to do about 15,000 queries a month for free. So it's actually pretty generous. You can actually do quite a bit because again, it's not, if you have a binary file that has a lot of data in it, this is just the text. So if you think about characters, actually, you can get a lot in there. And after that, you can actually grow with us. If you go back, you can buy bundles that give you more size and more queries a month as you scale with your use case. Again, generally, the way that the retrieval model works, again, it's every sentence and then the query itself gets an embedding. It's encoded into a vector of embeddings. And so think of it as a nearest neighbor algorithm where you get the query and you say which sentences that were indexed at the beginning matched closely to that set of sentences and retrieve the most appropriate sentences, right? So the indexing essentially says you have to create an embedding for each sentence and you have to store it in this. It's called a vector store. There's things like, there's a couple of open source projects for this and a bunch of different algorithms that I'm not going to get into now that help you make that matching really efficient and fast when you want to actually do the query. All right. And we have, by the way, we have some Vectara people here in the room that probably know a lot more about this than I actually do. So you can ask them at the end too. Feel free to do that. Okay, so let's look at a query, right? So we want to search something now, again, this is a example of this is in JavaScript, not in Python, but you can do it again in any language. So the way we form the query for the API is we have a query string over here. This is just the text of the query that you want. There's a couple of parameters. I'm going to walk through some of them, not necessarily unless you guys are interested, but not necessarily all super important. But you can define, of course, the number of results you want to get back. If you want to do pagination, you can also specify the start of the result and show other results later on. The corpus key is actually not shown here, but it's a definition outside of this particular thing that shows the corpus ID and the customer ID to identify the corpus. And then we have this thing called context. And the context essentially is, usually when we return a result, there's two considerations. One is, how do I show it? And we'll see that in a minute. How do I show it to a user? Usually if you show us just a sentence, it's a little bit out of context. So we allow you to add a couple sentences before and a couple sentences after, and the start tag and the end tag are text things that you can add that will return with the query, so you can like bold the matching piece, but you can see the rest of the sentence in context of this. So we'll see how that works. That's how you define these guys. And then you can define what summary you want to get. So again, how many results you want to get to be included in the summary. And we have a sort of a prompt name for our, I mentioned the growth plan. I'm sorry, I didn't mention the scale plan, which is if you go enterprise and you want a lot more features that we have for the scale plan, and you can actually change some of the prompts. That's one interesting feature of the scale plan. And then you can actually have responses go in different languages, which is kind of interesting too. And then essentially when you call the API, you have the headers, you have the URL, you have this body, and you just call it the same way and you get the response. How the response looks like is complicated to show on a slide, so I'll show you that in real time in a minute. But just generally, that's how the query works. Very simple. You get the resulting documents that we've seen in the AskNews, and you get the summary. Okay? And building a UI, so I think it's very easy to call the API and display it in like a JupyterNotebook and an example. Building really modern UI is actually kind of more difficult unless you're a really kind of a Node.js expert. And so we actually built another open source project called Vectara-Answer, really, really great project to sort of help you with that if you want. Again, it could be used as an example of how to do querying if you want, but it can also be used to build a first version, a really fancy first version of your application. And so, so let me go and show you that. So I'm going to go back to this and go to Vectara-Answer. So in order to use Vectara-Answer, what we do is we have two configuration files. You specify the corpus ID, again, that you want. This is one is for the Yelp information and the customer ID. And there's a couple other, they're not all shown here, but if they have default, so I don't have them. But here I have Yelp reviews is the title of the whole app. There's a title called, on the top of the search bar, that's called AskYelp, and restaurants in St. Louis, because I filtered it for St. Louis. And you can define a default language for the response if you want, and a couple other parameters. And what you do is you define these parameters. In this case, we have, by the way, you saw at AskNews, we had different sources like BBC, NPR, etc. Here we don't have them, so we just have this as empty. And then you can define, if you saw those 4 questions, you can also kind of curate questions if you want. You don't have to, but it's kind of nice to see that. And so if I go back to my AskNews example here, again, I can just run this. And again, it generates a Docker image to make it convenient. Docker image is really useful because, everybody have their own environment and sometimes it doesn't work. So it's a really nice way to isolate specifics of your own example. So this is our AskYelp example, as you can see here. I'm going to make it smaller a little bit so we can see. You see we have the AskYelp, which we saw in the configuration. We have the restaurants in St. Louis. So I can ask, for example, who serves the lobster bisque, right? It'll be fun. So again, it picks a bunch of documents and restaurants that have reviews about this topic, right? And says, oh, Vegas and Locks and the unnamed restaurant from search results 1 and 2 respectively both serve lobster bisque. So again, given the information it has, it will give you a response that summarizes that information. So one thing here is that we asked the model to use, as you can see, 2 sentences before, then we have this sort of bolded thing, and then we have 2 sentences after. But the summarization, I asked it to actually, there's another parameter, asked it to have like, I think 3 or 4 sentences. So we may not see this unknown restaurant comment here because of that. But we can try, I can try to change it. Let's see. See summary, num sentences for summary. Let's make that 2 as well. And see if we can run this again. Let me see that. Let's try that. This is a real-time demo, so for better or worse, that's what happens, right? All right. Is not mentioned. Oh, that's weird. Okay, I don't know. I'll take a look at that. Let's look at another example. Maybe it works better. Which restaurant is best for kids? Let's see if that works out better for us. Their favorite recommendations for kids, or Charlie restaurant is the family restaurant. So you see that there's very clear information here about it. Kids eat free, etc. Great place to take kids to have dinner and just sit down and chat. So again, this is a really nice UI, but sometimes you have to play for your particular application with some of the parameters to make sure that it hits the right performance. I'm going to go to network here and run this again here. So for those of you who don't know, this is called the inspect portion of the browser, and it's a little trick for developers that you can look at what's going on. So what I see here is I'm going to look at this last query. And what you see here is this is the request. So remember I showed you this on a slide, right? I'm going to make this a little bit bigger. You can see, hopefully. Maybe a little smaller, it's just too big. But you can see that there's a query here. And we have this context config, which says how many sentences before, after, etc. The corpus key, which I showed you earlier, that has the corpus ID, customer ID, etc. Number of results, and then the summary configuration. So this is what the query looks like that we send out, right? We saw this on the slide, and it kind of matches what we thought it would be. Now, the more difficult thing to show on a slide is the response. It's kind of a long-winded thing, but I wanted to show you this here. So we have a response set, which has a set of responses, like the name says. So the response is just a list of items. The first item here has this text. This is your score that you asked about. Usually it's ranked by the score, so this will be the top result. And it has all the metadata that I asked it to add here, including the metadata that is default, which is the document language and the offset and the length. This is where the text was in the document itself. Now I have a document index, which I'll explain what that is in a second, but keep a pin on that for a second. And then I have the second result, which is this text with a little bit of a lower score, all the metadata, etc. 3, 4, 5. So I have these results. And then I'm going to go down until I see, and you can see every one of those has a document index, which is just a numeric value. And if I go down to 10, probably here, then I have a document section. And so the document ID refers to these documents in order. So if you had document ID, document index, 0, it'll be this document. So now you know what the ID of the document is and what the metadata of that document is. So if you want to refer to the actual document itself, and the reason we build it this way is because some results might be from the same document. You might have multiple results from the same document. So just for efficiency, it's structured this way. And you have some of these documents that are necessary here. And then you have the summary section, which essentially gives you the text of the summarization that came out as a response, and the language, etc., some of the things that are there. So that's really how the response looks, and I'm sorry, this could not be done on a slide, so I thought it would be easier to explain in this way. All right. So the score is coming out of the retrieval model. And I want to mention, actually, it's a good thing to mention another thing here, which is the retrieval model has actually two components. One is the neural semantic search engine, which has its own score. And it's a score, I mean, correct me if I'm wrong, I think it's between 0 and 1 in general for the neural search. And so it's a score that tells you how much relevant it is. But we also recently added an interesting feature called that combines what we call hybrid search. So neural search is a very powerful thing. If you know more about this, it's like it can understand the intent, and it can don't have to remember all the keywords you have to match and everything like this. So it's very powerful. It works in multiple languages. But there are some cases where neural search doesn't actually work really well, where especially for single keywords, where you want to look for Apple Watch. No, that's not a single keyword, sorry, but like a term that's really specific. And so hybrid search actually combines both of these things together into a single search result that we will provide. So you don't have to use that. Again, you can choose to use it or not to use it, but it's actually a very powerful thing that helps you get much better results, and it's not easy to do otherwise, actually. And so I think that's really all I had in the presentation.